Good morning. Let's start today's lecture. Today we are going to continue the theme which was started in previous lecture, and title of today's lecture is Quadratic Surfaces. What does it mean, quadratic surface? The surface in the space which defined by the equations, which is a polynomial of second order, is called quadratic surface. In general case, this equation which defined quadratic surface has the following form: the sum of the squares of three independent variables plus twice cross product these variables xy, xz, yz, which multiply on some constant def, and plus linear part, which is form 2gx plus small mistake. To fy plus to ez plus j is equal 0. This general equation can be reduced to the one of the canonical forms. One of them, a prime times x square plus b prime times y square plus c prime times z square is equal to some constant d prime. And other canonical form is the sum of the squares of variable, one of two variable. For example, first two variable x square and z square, which was multiplied on some constant a prime and b prime, is equal c prime times z. The method of reducing the general equation to the one of the canonical form is the same as the case of the curves of the second order.
Excuse me.
And yes, maybe question?
For 2fy plus 2ez plus j, I think we have coefficient
f2gx. Thank you. A, B, C, D, E, H. Thank you. Mistake, yes. H.
G, H,
I, yes.
Yes.
I and plus J, yes.
Yeah.
Plus J is equal. Yes. And we have many letters. And as a rule, use the one letter A with indices. For example, A1, 1, x squared plus 2a 1, 2, y squared plus...
Sorry, Professor.
Yeah, I'm sorry.
What you're writing now is not visible at all for us.
Okay. This, as a rule, use the following form. Use one letter A with two indices. The first indices mean the number of the variable. For example, a11 times x squared plus a22 plus y squared plus a33 times z squared plus 2 a12 xy plus, good morning, 2a3 times xz plus 2 times a23 times yz plus 2a1 times x plus 2a2 times y plus 2a3 times z plus a0 is equal 0. And in this form, the part which contains quadratic terms is called quadratic form, and we can correspond to this form some matrix which the matrix with elements A11, A12, A13, A12, A22, A23, A13, A23, A33. Some symmetric matrix which calls the matrix of quadratic form, which correspond our quadratic surface. And this part of equation of the quadratic surfaces can be rewritten in the following form. I can multiply this matrix on the vectors on the from the right side on the vector which coordinates x, y, z, and from left side on the corresponding row vector which has the same coordinates. And after multiplication, these three matrices, we obtain the quadratic form of our quadratic surface. And in this formalism, we can code this matrix by the letters G. These vectors may be x bar, and these vectors x bar transpose. And this equation can be rewritten in the following short matrix form.
All right.
Yeah.
In the middle matrix, you have wrote A12, and it should be A21. Yes.
We have the symmetric matrix, and this element and this are the same. I see. I stress this fact using this notation. The symmetric matrix.
I see, sorry.
And yes, and in the equation we have the coefficient 2. Is consequence the fact we have the two matrix elements which are the same, and after multiplication this matrix on these vectors on the left and right side, we obtain twice the same element a1, 2 x y and the same element a1, 2 xy. For example, we obtain the same, we can multiply. We can do the following simple exercise. Let's multiply this matrix on this vector, and we obtain the following column vector a11x plus a12y plus a13z, a12x plus a22y plus a23z plus a13x plus a23y plus a33z. And we multiply these vectors on these, and we obtain the following sum. This product on this on this, and this on this, and we obtain a11x squared plus a12xy plus a13xz. We multiply x on the first element on this column. We multiply y, the second element on this column, and we obtain a12 yx plus a22y squared plus a23 yz plus the last element we multiply on the second matrix element of column vector of column matrix, and we obtain the following expression: a13 zx plus a23 zy plus a33 z squared. And we have the following, the same element, this one and this one. The multiplication of the numbers is commutative, and this element equals this. This element the same as this, and this element also the same. And we obtain exactly this expression.
Professor, why the last x is squared?
X, yes, y x squared?
Last one. Last one, a33.
A33. I'm sorry, z squared.
Yeah.
Okay, thank you. Z squared, yes. Z squared. We multiply z on a33z.
Yes.
And we obtain z squared, yeah. Thank you. And some explanation, this fact, why this coefficient are twice, and why this matrix is symmetric. This matrix formalism, enough short form for recording of our reasoning, and enough convenient for using in the calculation. But this recording and the usual recording are the same and equivalent. And let's continue. And now we consider some example of surfaces of the second order. And the simplest example is the sphere. What it means, sphere? Let's fix some point C with coordinate A, B, C in the space. And the sphere is defined by the condition. The sphere is the locus of the point. The distance between each of this point and our fixed point C is a constant. The distance is a constant. And let M be arbitrary point in the space with coordinates x, y, z. And let the distance Cm is equal some fixed value r, small r. And let's reduce the equation which defines such point in the space. We can consider the vector Cm, and this vector has the coordinates x minus a, y minus b, z minus c. And the square of the length of these vectors is equal to the dot product of this vector on itself, the scalar square of these vectors. And by definition of the geometrical locus, which is sphere, this distance is constant, and distance is equal r, and this square of this distance is equal r square. And scalar product is a sum of square of coordinates of this vector, and equal x minus a square plus y minus b square plus z minus c square. And we have the sphere. We have the sphere in the space. And center, the point C is called center of this sphere. This equation we can rewrite in the following form: x squared minus 2ax plus a squared minus 2by plus z squared minus 2cz plus a squared b squared c squared minus r squared is equal 0. Let's denote this term by d prime, and we obtain the equation in sphere in the following form: x squared plus y squared plus z squared minus 2ax minus 2ay minus minus 2by minus 2cz plus d prime is equal 0. You can change the sign on plus, and we obtain the general form of the sphere in the space, namely, these coefficients can be arbitrary, and these coefficients also can be arbitrary, but in some case we can obtain the empty set or one point. For example, if in this equation, the term in the right hand is negative, the set of the point which satisfies this equation is empty. For example, if we have the equation x squared plus y squared plus z squared plus 2 is equal 0. Easy to see that we have no point which coordinates are satisfy this equation, because this term is positive and we are adding other strictly positive term, and we must obtain the 0. We can obtain, we haven't the points which have coordinates which satisfy this equation, and we obtain the empty set. And in the case when this term is equal 0, we obtain one point in this case, and sphere degenerate in one point set. In this case, sphere coincide with the center of the sphere. Only one point. Only one point. This equation is the same, and in some cases this equation is defined the sphere. In other cases, it can be one point set, and this equation can be defined empty set at some point. And let's continue and consider other example of the surfaces of the second order. The next example.
Professor,
Yes, question? Yes, yes.
sorry, why is the last equation the general form of a sphere? Why?
Why is this equation a general equation of the sphere?
Yes.
Yes. Sphere is obtained by the center of the sphere and by the distance. And this datum is uniquely defined sphere in arbitrary coordinate system. And we obtain the general equation of the sphere in this form. We can rewrite this equation in this form. After some simplification, we obtain this equation. And we can, doing the inverse calculation, for example, we have this some equation plus we can rewrite this equation in the following form x plus a square minus a square plus y plus b square minus b square plus z plus c square minus c square plus d prime is equals 0. And finally, we obtain the following equation. Is equal a square plus b square plus c square minus d prime. And when this term is positive, and in this case, equal the square of some positive number r, where r is root square from this expression. And in this case, we obtain, if this term is strictly positive, we obtain the sphere. If this term is equal 0, we obtain one point set. And if this term is negative, we obtain the empty set. In this case, the empty set is called imagined sphere. In the complex vector space, we obtain the sphere, but with imagined coordinates. And in the real world is an empty set. But as a rule, this all cases is called sphere, and consider as sphere, but in the case of negative free term, we are using the term imagined sphere. And we obtain this arbitrary, the equation of this type is define the sphere. And first calculation show us that if we have the sphere in the space, we obtain the same equation which defines the sphere. And we can consider, and this reasoning proved the fact that the equation in this form is defines the sphere in the space. Do you understand my explanation? Mm-hmm. Okay. And let's consider some other examples. Cylinder. What does mean cylinder? Let's consider the same equation in the space, such form, but let's suggest that the term contains the variable z absent. And in this case, we obtain the equation some second order curve in the plane. Yeah, question? For example, let's consider the equation, for example, in the form x square divided a square plus y square divided b square is equal 1. in the plane, this equation defines the ellipse in the plane. Let's we have plane x, y, z, and we obtain ellipse in the plane. But if we consider this equation in the space, we must consider the point in the space with coordinates x, y, z, which coordinate and we consider such point which has the coordinates which satisfy this equation. For example, if z is equal 0 and let p prime be the point with coordinates x, y, 0, such that x and y are satisfy this equation, and we obtain some point p prime on which lies on our curve, and let's fix this point x 0, y 0. And let P the point which has the same first two coordinates x0 as the point P prime, but the third coordinate z can be arbitrary. And this point lies on the straight line which pass through point P prime and parallel axis OZ. Easy to see that the coordinates of this point are satisfied this initial equation, because in this equation the coordinate z is absent, and we can suggest that z as coordinate can be arbitrary. And we obtain the effect this all point of the such straight line which parallel to axis OZ and pass through point of some point of our second order curve is also lies on the surface, on some quadratic surface which defines this equation. And we obtain the surface which is called cylinder. This infinitely surface in the direction of OZ axis. And in other cases, if we have the arbitrary equation of the second order curve, a x squared plus b y squared plus 2cx y plus dx plus ey plus f is equal to 0. In all cases, we obtain the cylinder. But equation cylinder can be more complex form, we can rotate our coordinate system, and in arbitrary case, the problem to define the cylinder can be enough complex. But in the cases when one of the coordinates is absent, in this case, easy to see that we obtain the cylinder. For example, if we have the equation y squared is equal to px, and in this case, in the plane, this equation defines the parabola, and we obtain parabolic cylinder. In the case when we have the equation of the hyperbola, we obtain hyperbolic cylinder, and so on, and so on. And second example, if no one or more example of the cylinder, we obtain some cylindric surfaces, and the surfaces of the second order, cylindric surfaces which correspond to the curve of the second order, to the parabola, hyperbola, and ellipse, and ellipse. And ellipse. Okay, let's continue. Consider our example. And let's introduce some new notions. Trace and contour of surface. Definition 1. Yes, the question, yes.
How did you obtain the general form of cylinder?
Repeat please, what about cylinder? What's the question?
How did you obtain the formula?
The arbitrary formula for the cylinder. This formula can be enough complex, but in the case the cylinder is the form when one of the coordinates is absent, we obtain simplest example of cylinder. If we rotate the coordinate system, cylinder can be written enough complex form. For example, we have the equation x square plus y square is equal 1, and let rotate one of the coordinate x. Let x is equal x is equal, for example, the new coordinate x prime is equal x is equal x prime divided root square 2 plus y prime divided root square z prime root square, and y is equal x prime divided 2 minus z prime divided 2, and z prime is equal z. Z prime. Z is equal, and y prime is equal y. We have such cylinder, and x, y, and we rotate this coordinate system, and we rotate, and our cylinder rotate in the space, and in the new coordinate system we obtain the following equation: x prime divided 2 plus z prime divided 2 square plus y square is equal 1, and we obtain x prime 2 x prime square divided 2 plus y prime 2 divided 2 plus x prime z prime plus y prime is equal 1. And we obtain the following equation for the cylinder: x prime square plus y prime square plus 2x, z prime square, z prime square, xz z prime square plus 2x prime z prime plus 2y prime minus 2 is equal 0. And we obtain the new equation of the cylinder in the enough arbitrary form. And
sorry, Professor. You wrote trace and what?
Wrote
Trace
yes,
and on the top of the board.
And
trace. You wrote after you wrote lecture quadratic surfaces. You wrote
trace. Trace and contour of the surface. And now I define this new notion. Yes, okay.
You wrote x equal x prime over square root of 2. How did you obtain this one from x squared plus y squared equal to 1?
Now, we start with such a cylinder surface. And
yes.
What does mean this cylinder? We have a circle, and we have the cylinder which has the following form. We have some coordinate system, and in the plane x, y, we obtain the circle. And we obtain the cylinder which obtains a straight line which pass through this circle, and this straight line are parallel to the OD axis. This cylinder is defined by this equation. In this equation, the coordinate z is absent. And the same as a earlier considered picture. We have some equation. And I suggest to rotate the coordinate system. We rotate this to coordinate, and the cylinder change this position. We obtain, in the new coordinate system, we obtain the cylinder which has the following direction of its straight line. X, Z, I rotate on the angle which equal 45 degrees, and our rotation contour moving clock head, and maybe for example, we obtain the same cylinder on this direction, the same cylinder. And I would like to obtain the equation, this cylinder in the new coordinate system. The rotation, I'm sorry, this rotation against x, y, x prime, y prime. We obtain the same rotation. And in this case, we obtain the following formulas which expressed the old coordinates x, z in terms of the new coordinates x prime, z prime. We obtain the following formula. And in the new coordinate system, we can rewrite this equation in the new form. We substitute the new coordinate in this equation, and we obtain the following equation. The equation of our cylinder in the new coordinate system, and we obtain enough complex expression. Do you understand? And if we have such expression, we must rotate the coordinate system, and we can reduce this complex equation to the enough simple. And in this case, we can prove that this equation defines this some cylinder. We can some sufficient condition for the equation is define a cylinder, but this problem to kill the some coordinate. The idea, this expression is following. We have these three terms, and we must using rotation and kill this term which contain cross product of two variables. And after reducing our equation to the canonical form, we obtain the canonical form a prime x square plus b prime y square is equal c, or a prime x square is equal c prime y. One of these cases, we obtain cylinder. And the problem to reduce the arbitrary equation to the canonical form. After them, we can understand have we cylinder or not, or haven't. Do you understand that? My explanation.
Professor, sorry, the last part I didn't understand. What is it? A prime x squared plus b prime y prime equals c?
Okay, the main theorem, the theorem is the same as in the case of the curves, asserts that the arbitrary equation, arbitrary equation of the second order surfaces can be reduced to the one of two canonical forms. One of the two canonical forms. First canonical form, a prime x square plus b prime y square plus c prime z square is equal d prime. And the second canonical form, a prime x square plus b prime y square is equal to c prime z. We have one of the two canonical forms. And if the first canonical form, the coefficient c prime is equal to 0, we obtain the cylinder surfaces. Maybe elliptic or hyperbolic cylinder. And in the second case, the variable b prime can be equal 0. And in this case, we obtain a parabolic cylinder. This main theorem guarantees us to, after reducing our arbitrary form of the surfaces to the canonical form, we can understand have a cylinder or not. In this case, the equation of the cylinder is canonical. In this form, one of the variables can be absent. And in this case, we obtain the cylinder. What this answer on your question?
Okay, thank you.
But if we have arbitrary equation, we cannot understand what this equation, what the surface is defined by this equation in arbitrary case. We have some sufficiently condition, and we can check this condition. For example, if we have the matrix of quadratic form, we can understand what this matrix, what the surface is defined this matrix. If we have arbitrary symmetric matrix, this matrix can be reduced to the diagonal form. And this diagonal form can be have three positive elements on the diagonal A, B, C. And if this non-zero element, we obtain the second standard form. And how to obtain that these elements are not equal 0? We can calculate determinant of this matrix. And if this form has a determinant which is not equal 0, we obtain this element, all elements are not 0. And in this case, we can't, and in this case, our equation is not cylinder. Is defined some surfaces which is not cylinder. But if determinant is equal 0, in this case we can obtain, for example, parabolic surface, and we can obtain the cylinder. And if we consider other invariant of our form, we can check have we a cylinder or not. But this reasoning found on some algebraic technique, and this technique we consider some later. But the simple answer is the following: we must reduce the arbitrary equation to the canonical form, and after them we can easier understand what the surface we obtain, what the surface we have. Yes, let's continue. And definition, trace and contour of the surface. We have some surface, and we can obtain intersection of our surface with one of the coordinate plane. And intersection of coordinate plane and our surface is some curve, and this curve is called trace of the surface. For example, we have a sphere with the center in the origin of our coordinate system, and the equation of the sphere x squared plus y squared plus z squared is equal r squared. And let's consider intersection with sphere and coordinate plane x, o, y. This coordinate plane. The equation of this coordinate plane z is equal 0, and intersection of these two surfaces, plane and second order surface, is a circle x squared plus y squared is equal 1, and this xy trace. And
sorry, trace means some kind of curve?
Yes, the trace, the coordinate plane cuts our surface.
Oh.
We cut our surface.
Yes.
And intersection is the trace, the intersection of our two surfaces. The edge of our surface, which cuts this, the plane cut our surface, and edge of the cutting is a trace. The definition the curve in which coordinate plane cuts the surface. The surface is called trace. It's called trace of the surface. Surface in the plane. Example: XY trace. In this case, we obtain XY trace circle and XZ trace is circle and YZ trace and also circle. And the definition 2. The curve in which plane parallel to the coordinate plane cuts the surface is called contour. We have the same XY contour, XZ contour, and X square contour, but we have unique XY trace, but we have many XY traces. For example, in our example, we have XY trace, which is defined by equation x squared plus y squared is equal 0. But XY contour, we have many XY contours. For example, let's cut our surface by the plane Z. For example, R is equal 5. And in the right side, we have 25. And let Z is equal 2. Z is equal 2. And in this case, we obtain that intersection of these two surfaces is equal x plus y is equal 21. We have the circle, but radius of the circle root square from 21. In the case when Z is equal 5, we obtain 1 point set. 1 point set, the circle of 0 radius in this case. And we obtain x plus x squared plus y squared is equal 0. Is equal 0. And we obtain only 1 point intersection of these two surfaces. And if the plane is equal equation Z is equal some numbers which are greater than 5, we obtain the empty set as intersection. Okay, these contours and traces help us to understand what the surface we have, we consider. And let's consider.
Sorry.
Okay.
I understood what the trace means, but the contour didn't understand. Yeah.
The difference between contour and trace.
Yes.
Yes, the trace, the curve which cutted by
Plane.
the coordinate plane, by the coordinate plane. But the contour is the same, but contour is cutted by the plane which parallel to the coordinate plane. We have many, infinitely many plane which parallel coordinate plane. We can shift it, moving the coordinate plane parallel to itself, and we cutting many contours. In this, in the case of the sphere, we obtain infinitely many circles, which have various radius. This radius changing from maximal radius in our case 5 to 0 in both directions. Okay, and let's consider many trivial examples. The list of the surfaces. Cone, ellipsoid, simple hyperboloid, double, elliptic, and the last hyperbolic. The list of the basic surfaces. Cone, ellipsoid, simple hyperboloid, double, elliptic, we have the following list of the basic surfaces of second order. And on the right hand, we have the canonical equation of these surfaces. And our goal to understand what the form has these surfaces. And let's start from the first example, cone. We will use the method of the traces and contours. And easy to see, if z is equal 0, the trace x, y trace of this surface is a point origin of our coordinate system. But if z is not 0, for example, let z is equal c. Z is equal c. And let's consider xy contour of our surface. And in this case, the intersection we obtain x squared divided a square plus y squared divided b square is equal 1, and we obtain ellipse. If we consider the value of z which greater than c, we obtain the ellipse which have the similar this, but has the great size, and we obtain the following picture: x, y, we obtain the following surface, which called cone. And what the contours of these surfaces we can obtain if we fixed. Let's consider the x z trace. In this case, we obtain the following system of equation. The coordinate plane xz is defined by equation y is equal 0. Y is equal 0. And in this case, we obtain x squared divided a squared minus z squared divided c squared is equal 0. What does it mean, this equation? This equation can be written in the form x divided I minus z divided c times x divided a plus z divided c is equal 0. And this equation defines two straight lines which intersect in the origin of a coordinate system. And x, z, we obtain two straight lines. to straight line in this case. If we are moving this plane and let's put y is equal some constant c. For example, y is equal constant equal b. In this case, we obtain our equation is equal -1, or I can change the signs in this equation, and we obtain z square c square minus x square a square is equal 0, and we obtain hyperbola, and section of the conus in this case is hyperbola. Also, we can obtain as section the parabola in this case. Exercise. How to obtain parabola as a contour. Of a cone.
I'm sorry, Professor.
Yes.
When y was equal to 0, what did we obtain? What was the section?
Y, we consider the contours, xz contours. X, Y, Z. Our cone. Maybe let's consider the most simple cases when A, B, C is equal 1, for simplicity. And I suggest to consider the contour x for example x maybe y yz maybe xz, maybe xz contour, xz, xz, and I would like to cut our surface, but y is equal c. The plane y is equal c. This plane is parallel to the coordinate plane x 0 z, x0 z.
Professor, you're solving the example right now?
Yeah, in this example, we obtain x squared plus y squared minus z squared. I'm sorry, 0, 0. Y is equal, c is equal 1. Z is equal 1. And if we substitute this equation, in this equation, we obtain the following equation: x squared minus z squared is equal -1. What does mean this equation? we obtain the equation of hyperbola. We can change the sign, and in this case, we obtain the following equation. Z square minus x square is equal 1. We obtain hyperbola. And easy to see, if we cut our surface by the coordinate plane which parallel to plane to the plane x over z, we root this cone, and we obtain this such the section which we obtain after such cutting are the hyperbolas. Do you understand that explanation?
Yes, Professor. Thank you.
We obtain the exact formula, and this formula is define hyperbola. Yes, okay.
Thank you.
Okay, and but exercise. Obtain the parabola in this case. How to obtain the parabola? How to cut? But it's most hard case because we can't parabola using only contours and traces. We must consider the more complex plane, which not parallel to the coordinate plane, which plane must be parallel to the one of the straight line which defines the direction our cone, namely, for example, if we consider, for example, equation I have time, and I suggest to consider this case as exercise and obtain the plane which cuts our cone, and in the section we obtain the parabola. How to choose such plane which cuts our surface by parabola. This exercise. And the next lecture we ending the consider of this example. And briefly, I try to understand the form of these surfaces. The second example, ellipsoid. If we consider traces of this ellipsoid, traces by the coordinate plane x 0, y. Z is equal 0. We obtain ellipse. If y is equal 0, we obtain also ellipse. And in the last case, we obtain also ellipse. We obtain three ellipses in the coordinate plane. And the form of this surface such that in the second case what does mean simple hyperboloid? If obtain z is equal 0, we obtain ellipse. In this case, y is equal 0, we obtain hyperbola. And in this case, we obtain also hyperbola. And the form of this surface is the following. Ellipse and hyperbola. And we obtain simple hyperboloid. In this case, we change the sign. And how to change this form? In the case when z is equal 0, we obtain empty set. No, empty set. If z is equal c, we obtain one point set. 1 point set. And the section, if y is equal 0, we obtain hyperbola, and in this case we also obtain hyperbola. And we obtain double hyperboloid. Double hyperboloid. Elliptic paraboloid. In this case, when z is equal 0, we obtain 1 point set. When z is greater 0 is positive, z is positive, we obtain ellipse. And if x is equal 0, we obtain parabola. Y is equal 0, we obtain also parabola. And we have the surface which has the following form. This contour is ellipse, and this contour is parabola. And this trace, both trace parabola. And the last surface, hyperbolic paraboloid, or other words, the saddle. What's the form of the last surface? Easy to see. If z is equal 0, we obtain two intersected straight line. When c is positive, z is positive, we obtain hyperbola, and negative also hyperbola. If y is equal 0, we obtain parabola, up-directed branches. If x is equal 0, we obtain also parabola, but down-directed branches. Y is equal 0, x, y. Y is equal 0, we obtain the parabola which directed. If x directed 0, we obtain down. Maybe I suggest x, y, and in this direction. And this direction, one of the direction, such an other direction is the same, and we obtain this straight line which has this form. Sorry, straight line, the saddle. And the next lecture we finished to consider this example, and maybe we can understand better the form of the surfaces. Any question?